This question, it says that Stephen Hawking has found, talks about black holes and amounts a small amount of radiation, and it causing them to slowly evaporate over time. According to Hawking, the mass of a black hole obeys the differential equation dm over dt equals k over negative m squared. So this basically means that the rate of change of mass is inversely proportional to the square of the mass. So part A says use separation of variables to find the general solution. So to find the general solution, we start with our differential equation, negative k over m squared. We're going to separate our variables, so we end up with m squared dm is equal to negative k dt. We integrate both sides, and so I end up with m cubed over 3 is equal to negative k t plus c. So I'm going to multiply both sides by by 3. So I end up with negative 3kt plus 3c. I'm just going to replace that 3c with a different c and then solve for m. So I have, I'll call that c2 minus 3kt, the cube root of that, and this represents the general solution for this equation. Okay, and I'm going to plug in there my value for k. So when I plug in my value for k, I end up with 3.78. So that k value times 3 times 10 to the 23 times by t. Okay, and that's my general solution. So that's part A. Part B is a little bit more involved here. It says after supernova, the remnant of a star collapses into a black hole with an initial mass of 6.00 times 10 to the 31. How long will it take for the black hole to evaporate completely? Okay, so we're given two values here. We're given the mass at 0, t equals 0, and that's going to be 6.00 times 10 to the 31 kilograms. And we're also being asked to find the time, m of t. So we're trying to find the time when the mass is 0. Okay, so let's use the initial condition to find the c first. So the mass at time 0 is equal to 6.00 times 10 to the 31. And that's going to be equal to this expression here. I'm just going to slide this down a little bit. It's going to be equal to C2 minus 3.78 times 10 to the 23 times 0. So that's all just going to be 0. Okay, so C2, the cube root of C2, is equal to 6.00 times 10 to the 31. So the value of C, it works out to be, when I cube both sides, I end up with, it looks like 2.16 times 10 to the 95. Okay, so some big mass. That's going to be our C value in this equation. So then writing my expression, m of t, so this is my function, the mass as a function of time is equal to the cube root of 2.16 times 10 to the 95 minus 3.78 times 10 to the 23t. And we want to find the time when that mass is equal to 0. Well, that means then that the inside must be equal to 0, so I can solve the equation for the inside equal to 0. So I'm going to isolate the t value. So I'm going to divide both sides by whatever that constant is. So it's going to be 2.16 to the 95 divided by 3.78 times 10 to the 23, and dividing those out, we end up with the time works out to be 5.71 times, it's a pretty big number, it's going to take 5.71 times 10 to the 71 years for the mass to go to zero. So all this mass to dissipate to zero is going to take a very, very long time.